Hello, welcome back. So, we are discussing about the degradation process of calcium oxalate, and we are thinking that how the corresponding weight loss can take place. So, this is a very simple plot of all these TG experiments. You can have the corresponding sample, only thing that you have to make the corresponding sample of calcium oxalate and put that particular sample in the instrument. And nowadays the automatic instruments can record this particular type of plot, where we find that, as I told you in one of our previous classes, that whatever amount of sample, it can be 15 milligram or it can be 10 milligram sample of calcium oxalate. So, we go for the corresponding heating process depending upon the crucible what you can have. So, the small crucible which can have the 15 milligram or 10 milligram of sample is heated within the furnace, but when we plot, the plot is the corresponding mass loss in percentage. So, whatever amount of sample you take, it is independent of the amount of sample, whether in a one single run you take 15 milligram of sample, in another run you take 10 milligram of sample. But when you divide the weight of the sample to this particular one, the scale goes to 100. So, we can go for 100. So, we start from a 100 percentage of that particular sample and we keep on heating the sample. So, this is the furnace heating scale, the temperature of that heating rate of the sample, if it is synchronized with time. You can plot this, that means x axis can be plotted in terms of the time also. So, you see for a particular sample from room temperature to 100 to 200 to 300 to 400 to up to 700, and the nature of the sample is known by the typical trace of that particular sample. So, is basically very much characteristic of that particular sample. You do not find two samples can have exactly same thermogravimetric plot. So, the plot is very much characteristic for that particular sample, and you see that up to 100 degrees centigrade you have a negligible weight loss, then 200, then 300, and all these things basically goes if we go for a 700 degree case. But above 100, what we find, what we have seen, and we will again discuss about the corresponding one for calcium oxalate and magnesium oxalate, that in this particular case the typical staircase like plot we do not see, because these are some real samples. Sometimes we get these for metal complexes, the polymeric samples, or any other solid samples, where we find that beyond 100 degrees centigrade, that means above 100 degrees centigrade, a monotonic change or monotonic decrease or the weight loss is monotonously going down and is basically only the slope is changing. So, after 100 degrees centigrade we get continuous weight loss of all these things till 500. After 500 it is again slowing down to till we reach 700. So, during this whole period of process of heating from 100 degree to 500 degree centigrade, what information we get from this particular type of plot is that the percentage of weight loss, it is only 100 is going down to 85%. So, 15% weight loss till a very broad temperature range is a very high temperature range of 700 degrees centigrade. The material is no doubt is very stable material, because 85% mass is still remaining at 700 degrees centigrade. That means, the 15% of these, that 15% can be your trapped solvent molecules, trapped water molecules, or some water of crystallizations, or some gaseous species like that of our carbon monoxide, carbon dioxide, or even if we heat some sulfate salt, the sulfur dioxide or sulfur trioxide can come out from that particular medium. So, these gaseous samples of all these products can only contribute to the 15% to the actual weight of the sample which is undergoing the thermal degradation process. So, until and unless you have a very discrete and very good horizontal lines, we cannot say that the sample is stable till 100 degrees centigrade. At least here we can say that the sample is little bit stable, that means it is 1% or less than 1% loss till 100 degrees centigrade. that is stable till 100 degree and it is more or less stable at this particular wet loss or mass change is between 600 to 700 degree centigrade. So, between 600 and 700 degree centigrade, because it is quite a bit wide range of temperature. So, if we want to dry the sample at this particular temperature range of 600 to 700 degree centigrade, what we find that the sample corresponding to this mass loss and the remaining sample what we can have, we must have a formulation for that, and we can say that the sample is stable in that formulation within this particular temperature range. So, what particular instrument we can use to record this particular thermogravimetric plot, that we will see. And in our first two classes what we have discussed is that we can have a thermobalance what K. Honda introduced, the first and historically important thermobalance, and these all will only the corresponding extension of these things. So, this is the thing, that means we have the corresponding beam, the corresponding balance beam, and this balance beam is there. At one hand you have the corresponding weight and the sample is going inside, and this particular sample is kept within a corresponding furnace, and furnace is basically electrically heated. So, this particular arrangement and putting the sample inside the furnace will be useful for recording your corresponding thermogravimetric trace. So, just now what we have seen, it is another one which is a typical example, again percentage starting from 100. So, it is thermogravimetric analyzer or the analysis, basically is the analysis. So, analyzer, the instrument what is doing that particular analysis is the corresponding analyzer, but is the analysis is TGA analysis, thermogravimetric analysis plot, and wet loss versus temperature plot is like this. So, here also not a very discrete or very sharp staircase like of arrangement, but from here basically we can have again some continuous wet loss curve we see, but at this particular temperature which is 350 degree centigrade, beyond that is 375 degree centigrade, or if we consider at 400 degree centigrade, 400, 500, 600 and 650 degree centigrade. So, from 400 to 650 degree centigrade we do not see any wet change over there. So, we use the instrument, we get that particular plot, and how we analyze this particular plot, we use that a more advanced one, that means the instrument which is coupled with that of your balance head. So, we have the balance head, then the coupled with these glass wires and all these things, and we have the sensor, that means the temperature sensing unit, that means what particular temperature is being sensed by the sample itself. So, we have the thermocouple, and this particular one is a controlling unit which can control not only the temperature, but also the weight in the balance. So, this furnace controller and this is the balance controller. So, this thermal controller can control the balance unit, and the furnace controller can balance the corresponding controlling of the corresponding temperature rise, and when these two are connected we go for the corresponding weighing thing. So, the information or the data what we get from this particular one is recorded and is ultimately plotted in the form of the corresponding TG thermogram, what we can analyze nicely for the different types of thermograms. So, one such thing is like this. So, what we have seen so far is the corresponding calcium oxalate monohydrate. Sample size is also known. Sample size is if we take 90 milligram of the sample, and heating rate is also 30 K per minute and in nitrogen atmosphere. So, in the nitrogen atmosphere what we find, just now what we are discussing about the same sample, and the apparatus what we use for thermogravimetric analysis, that means the TGA trace can also be coupled with the corresponding derivative one, but it is nothing but the corresponding one is that simply you plot the corresponding derivative one, that means the derivative of the corresponding mass change with respect to the corresponding temperature. So, this one basically we go for this corresponding change will be giving you a corresponding derivative plot. So, derivative plot has some good correlation with the TG plot. So, as we have seen in case of calcium oxalate, the wet loss of water of crystallization. So, this is the first step we get, that is the wet loss of corresponding water of crystallization, which will be around 200. So, it is stable up to 200 degrees centigrade. Then what we see, that at the particular temperature of 500 degree or so, we can have the corresponding formation of calcium carbonate with the evolution of carbon monoxide. So, evolution of carbon monoxide is not exactly 500, but is less than 500. So, is the formation of calcium carbonate and evolution of carbon monoxide, and what we are talking about so far, that is very important. And two things we are discussing, that you heat the sample or any other sample, any other analyte you can go for, either you heat it in air or oxygen, or you heat it in nitrogen. So, when the atmosphere is nitrogen, that is why when we are discussing the sample characteristics as well as the environment of the sample, because all these cases are a very important cases for a high temperature reactions, because all these thermal conversions are taking place at a very high temperature, and in some cases gases are coming out, and some inert gases like nitrogen or any other, that means argon. The sample at that particular high temperature should not react with this nitrogen, because if we heat that, and we all know that the metallic calcium or any other thing, if we heat at a particular temperature, it can also give you the corresponding calcium nitrides. So, we should be careful about all these formation, that means the reaction with that of your nitrogen. So, in nitrogen atmosphere, that means in inert atmosphere, this particular calcium oxalate what we have, and we give it in some inert atmosphere, and what we expect over there, that you have the corresponding calcium oxalate monohydrate. Then monohydrate is giving rise to simple CaC2O4, that means the dehydrated one plus water. So, this is the thing, that means at this particular temperature range, and if that is a very sharp one. So, at this particular temperature we can dry the sample, we get this as the corresponding one of anhydrous calcium oxalate. Then what we get, that at nitrogen atmosphere, no water, no air present and no dioxygen is present. So, this particular one in some inert atmosphere, that means it is neither in oxidizing environment nor in some reducing environment, but at this point when we have the anhydrous calcium oxalate, which is stable in this particular range of 228 to 298, but above 298 when we heat it, what we get at this particular temperature range of 398 to 420 degree centigrade, this particular one will decompose in a step which can give rise to the elimination of carbon monoxide. So, carbon monoxide evolution can take place over here, and in some of our future class, time permits, we will discuss the corresponding gas analysis of these processes. So, if some suitable technique is available, that means the corresponding chromatographic separation, if we can do that, the gas chromatography we can do on the sample, and if it is attached with some mass spectrometric analysis. So, we can go for GCMS analysis for these gases which is coming out from the sample. So, which is a very important information, that some part and which is also not a very useful gas is the carbon monoxide, which is coming out from this calcium oxalate, and we get the remaining one as your calcium carbonate. So, here we have this, that means your calcium oxalate, anhydrous calcium oxalate is slowly decomposing to calcium carbonate, and at this point your carbon monoxide evolution is taking place. At this point water vapor was coming out, and we have the stable calcium carbonate at this point. So, within this temperature range of 420 to 660 degree centigrade, we have stable calcium carbonate, and if possible we can analyze this for your CO. Then in the last step, this is getting degraded. So, calcium carbonate in a straight way is getting degraded to calcium oxide plus carbon dioxide. So, now this gas is coming out in this particular step of a temperature range which is above 838 degrees centigrade. So, above 838 degrees centigrade, what we see, what we find is your stability of your only calcium oxalate. So, this particular metal ion carbonate, like other metal ion carbonates, we can have magnesium carbonate, we can have barium carbonate, we can have strontium carbonate, because all these samples are very useful samples for the standardization of the thermogravimetric analyzers. So, here also again what we find that this CO2 can also be analyzed by GCMS analysis. So, identification or the scope is there to identify carbon monoxide in one step and carbon dioxide in any other step. So, anything, any biological process or any other thing where gas is coming out from the sample, we can analyze those gases, and the remaining sample or the solid what we can have, we can analyze. So, the furnace what is heating is going for the corresponding conversion, but the balance what is present in this thermogravimetric analyzer is that they are taking the weight. In one case it is the weight of this or the weight of the hydrated form. So, hydrated form your sample A, this is sample B, this is sample C, and this is your sample D. So, that is a very useful and a very good example of the conversion of a calcium bearing compound, one from A to B, B to C, and C to D. So, what will happen now to magnesium oxalate dihydrate? So, this is the corresponding. Now, once you know this for calcium oxalate very minutely or very useful way, now what we can see that in case of this particular sample what we find over here for magnesium oxalate, immediately we know that the elimination of these two water molecules. So, 2H2O will be eliminated at this particular step. So, this particular step is therefore giving rise to the elimination of two water molecules. So, the corresponding magnesium will be forming over here. So, this is the step where the magnesium oxalate is stable from 233 degrees centigrade to 397 degrees centigrade. So, this is our magnesium oxalate MgC2O4, which is anhydrous. This is your dihydrate, then water loss is taking place. This is your anhydrous form. Then anhydrous form is going to something like this, but what happens depending upon its different nature, that means the magnesium ion is different. So, what thermal reaction what we can write is MgC2O4, which is anhydrous one, which has been formed from the elimination of two water molecules. So, the previous information what we can have in our knowledge is that we can give rise to something which is a separate step for the carbon monoxide evaluation, and in another case it is the evaluation of carbon dioxide. But in this particular case, straightway this magnesium oxalate is giving rise to magnesium oxide. That means, here we do not have the corresponding presence of magnesium carbonate, because the magnesium carbonate will not be that much stable in this particular temperature range, which is above 397 degrees centigrade. So, 397 degrees centigrade is such a high temperature, and at that particular temperature we see that your magnesium oxalate is stable. So, at this particular temperature, so we can have like this of your calcium oxalate thing, that we can have a separate step, that means one more step where magnesium carbonate should be stable, but this is not happening. So, this is not stable at this temperature range. So, what we see and what we get is that magnesium oxide plus carbon monoxide plus carbon dioxide. So, in a single step, this is the solid residue what we will have in this particular whole range of this particular stability starting from 478 degrees centigrade. So, we have the solid residue. So, this solid residue will be here and these two gases. So, mixture of gases now the situation is getting little bit complicated. So, we have the mixture of gases will come out. So, there also we can apply the same technique of this particular GCMS analysis, because the gas chromatography, the terminology for chromatographic analysis is, we all know that the chromatographic technique is a separation technique. So, the gas chromatographic technique is the corresponding separation technique of the mixture of different gases. So, initially it separate or the corresponding distribution of the different gases you can have, then the mass spectrometric analysis we can do on the amount of gas. So, if we have the mixture of gases also, that can be injected in the GCMS instrument. So, that can initially separate into these two gases and that can find the corresponding amount of carbon monoxide and carbon dioxide. And what interesting information why you can get from there is that a mixture of gas which is in the ratio of 1:1. So, a 1:1 mixture of carbon monoxide and carbon dioxide is coming out due to the instability of magnesium carbonate at this particular temperature range, is a very useful information for the analysis of both calcium oxalate and magnesium oxalate. And this particular stability of these temperature ranges, if we find that at this particular 500 degrees centigrade. So, when the temperature is 500 degrees centigrade. So, at this particular temperature, so at 500 degrees centigrade here and at 900 degrees centigrade, if we do the thing, that means if we have a mixture of these two, since magnesium carbonate is not formed over there, is not stable at this temperature range. So, if we have a mixture of calcium oxalate and magnesium oxalate, which is our original problem, because our problem what was there is your hard water, and that particular hard water can have both calcium as well as magnesium in your thing, that when we have this hard water, so we precipitate out these two as the magnesium and the calcium. But now solely what we can do, we can analyze these two compounds at the presence of both calcium and magnesium. Only thing that what we can have the x percentage of calcium oxalate plus y percentage of magnesium carbonate, we have to find out. From there, depending upon the corresponding molecular formula and the molecular weight of the samples, what we weight out in the balance for the normal gravimetric analysis, we can find out the percentage of calcium and the percentage of magnesium present in the sample of your hard water. So, what we find over there is a very simple information, that if we have a mixture and if we hit the mixture without going to all these things, that means all these detail analysis and all these detail identification and characteristics of these samples, what we find that this particular one, that means at 500 degrees centigrade, if we hit this mixture of these two oxalates, we get that at 500 degrees centigrade, because we have seen that here it is the calcium carbonate. So, only calcium will get the weight of calcium carbonate and magnesium oxalate, because these two are stable at this particular temperature. So, this calcium carbonate and magnesium oxide are stable at this temperature, and if we take the weight, that means whatever precipitate you got, you heat it at 500 degrees centigrade in some oven and you take the weight. For what you expect, this particular knowledge or this particular information you must have, that at this temperature you will only get the weight of calcium carbonate and weight of magnesium oxide. And to check the particular percentage in terms of the amount of magnesium and calcium present in the hard water, we take the another help of heating the sample at 900 degrees centigrade. So, heating that particular sample at 900 degrees centigrade is also give rise to another information, because both of them can exist in simple oxides, that means calcium will be present as calcium oxide as well as your magnesium will be present as magnesium oxide. So, this give rise to the immediate information, and from the analysis of the amount of calcium oxide and the magnesium oxide of all these things and the comparison of the weights of the mixed precipitate. So, if we go for comparison of weights of mixed precipitates at these two temperatures, that means 500 degree centigrade and 900 degree centigrade, at those two temperatures will permit to determine the content of both, that means the calcium 2 plus as well as magnesium 2 plus content in the original sample. So, this is the real example of your analytical technique, what we can use to determine the calcium 2 plus and magnesium 2 plus in the sample of analysis, where we get this for your analysis, that by heating the sample to 500 degrees centigrade and by heating the sample to 900 degrees centigrade only tell us the amount of calcium and magnesium present in our original sample, that means the sample which is present in our hard water. So, that hard water sample handling is a very important thing, and the nature of these plots are also very much important, because once we have this information for the different species, that their thermal stability. So, any compound you can have and the temperature we can write. This can be your useful drying temperature for the precipitate, like that of your magnesium oxalate, calcium oxalate, or nickel DMG or aluminum oxynate. So, here we have from the plot what we can extract as data, that you have the calcium oxalate monohydrate, which is stable up to 100 degrees centigrade. Similarly, if we have on the right hand side, if we think like that, other compound, degree centigrade. So, other compound is your magnesium oxalate dihydrate now, which is stable, more stable up to 176 degrees centigrade. So, if we just compare these, so thermal stability of these two species we can compare by knowing the temperature of these two. Then we have the degradation, that means we get the anhydrous calcium oxalate, water is going out, which is within the range of 226 to 398. Similarly, anhydrous magnesium oxalate is also stable within the range of 233 to 397 degrees centigrade. So, what you find then, that the degradation of these and degradation of these is different. So, you have calcium carbonate in your hand, which is stable in the range of 420 to 660 degrees centigrade. So, this also gives rise to another horizontal space, but which is 480, a little bit higher, because you see most of the time your temperature range for the magnesium is a little bit higher, but this particular one is 850 is basically the temperature where we do not get the calcium carbonate, but we immediately go for the corresponding magnesium oxalate or oxide. So, the formation of this magnesium oxide which takes place at 480 degree centigrade. So, and up, that means and above, but where this particular calcium carbonate is stable. So, you do not get the corresponding formation of magnesium carbonate over here. So, for calcium oxide formation which is taking place at 480 and up, say up to 980 degree centigrade. So, these are all the corresponding data. If we do not have the corresponding plot as the thermogram, so we should know the corresponding analysis in this way, and you see that not only a single compound which is undergoing the corresponding thermal degradation, but it is transforming some useful species, which is also a very useful technique for the thermal analysis. And sometime we go for some technique where thermally we can go for some synthesis of some new compound, synthesis of some catalyst, which basically a useful technique nowadays the researchers are also using, which is known as hydrothermal synthesis. Just name, you just know it, that since we have this process of thermal thing, so thermal thing is there, then hydro is your water. So, what we know that any chemical reaction we can do or perform in making the sample of two analytes A and B, which independently we can analyze for their content, but if we mix these together, then we can just simply mix and stir it magnetically, we get a new compound C with along with some other byproduct D. But if we go for heating at a very high temperature in a closed vessel, so this will give rise to some information about high temperature reaction what we can have, and this high temperature reaction can give rise to the immediately that in solution the corresponding degradation pattern and all these things the reactivity pattern will be different. But if we simply heat the compound like making the thing or the industrially important compound like cement formation or the cement production or the cement synthesis in industry, that several oxides, carbonates and some useful material which can be heated to a very high temperature. So, if we get some time in our future classes at some time, particularly during the application process, we will find that how useful these reactions or this thermally activated compound formation is useful for synthesis of new and useful compounds. Thank you very much.